All right, chapter 4. We talk about chemical bonding. Put that reminder up there because I have forgotten to turn the recording back on, done the whole lecture and not recorded it. Chapter 4, chemical bonding. Exam 2 is going to cover chapter 4, 5, and 6. Well, that's 1, 2, and 3. 4, 5, 4, 5, and 6. All right. Those are the topics we're going to cover. They're just in there for general organization. All right, let me get this out of my way. Set that up there. Slide this over here. Okay. So what is a chemical bond? You may have some intuition about what a bond is, but that's not often good enough because scientists have been struggling with the chemical bond, the nature of the chemical bond, for a very long time. And it wasn't until Linus Pauling kind of pulled everything together and at least gave him a coherent theory behind what a bond is, how bonds work. And for that, he got the Nobel Prize in 1954. Simply put, a chemical bond is the force that holds two atoms together. It can be accomplished by a number of different actions, so to speak. It could be ionic. Right? You could have the purely electrostatic attraction between a positive and a negative charge and pull them together like sodium chloride. Or it could be covalent. And let me back up. Ionic bonds typically occur between metals and nonmetals. So anything on the left-hand side combined with anything on the right-hand side, unless they're really close together, right along that zigzag line that separates the metals from the nonmetals, those guys sometimes they tend to switch and act like nonmetals. Silicon's that way. Silicon's in the nonmetal side, but sometimes it acts like a metal. So if you're going to assume that an ionic bond forms between two atoms, a metal and a nonmetal, it's best if the metal is way over here on this side and the nonmetal's on that side. Then you're pretty much guaranteed an ionic bond. And to have that, what you need is a transfer of electrons, right? There's sodium, and there's a chloride atom. If we take an electron from here and transfer it to chlorine, right? These are neutral to start with. So now chlorine has a -1 charge, sodium has a +1 charge. Okay. And you know sodium is in the first column, alkaline metals. Any of those metals, when they're charged, they only occur in one form, +1 charge. And that's the reason. They only like to lose one electron. Whereas the halogens, they typically, when they charge, form a -1 charge. Fluorine, chlorine, bromine, iodine, they prefer a -1. And that goes back to the electronic structure. We did that, I think. Electronic structure. If chlorine accepts an electron, what does it look like, electronically speaking? It looks like argon. It looks like a noble gas. If sodium loses an electron, what does it look like? It looks like neon, electronically speaking. It has the same electronic structure as neon. And that tends to be what atoms prefer when they enter into a chemical bond, is they want to appear electronically like a noble gas. Sometimes that occurs by transfer. Sometimes that occurs by sharing. Right? So if you have oxygen bound to two hydrogens, right? Hydrogen only has one electron, right? Well, oxygen has how many electrons? Well, it has 8, but it only has 6 in its valence shells. Right? So we're only concerned with 6 electrons in the valence shell, right? If this one shares an electron here, and that one shares an electron here, and this one shares an electron, and that one shares an electron, you have 2 electrons makes a bond. And oxygen thinks, well, look at there, I got 2 electrons. 6 plus 2 is 8. I have my octet. You know, I look like neon now. Well, actually, it's this one and this one, right, on top of those 2. So 2 plus 6 is 8. That makes the octet. And all the noble gases, well, neon and argon have an octet. But when you get down to krypton and xenon and radon, you have a lot more space to fill. But they have a complete outer shell with electrons. And that's what they're like. Even though that electron did not pass to oxygen exclusively, right? And what about hydrogen? Well, it thinks it acquired that one, right, with this one. So it thinks it has 2 electrons in its outer shell. What does it look like? Not a clue. It looks like helium. Helium has 2 electrons in its outer shell. Its only outer shell. And same thing with this one. So even if they share electrons, they have the appearance of a complete outer shell, just as a noble gas would have. All right, now that's the practical. That's rationalization at this point. Why these bonds form to look like noble gases, but actually all the elements, their reactivity depends on either acquiring or sharing electrons or donating electrons in such a way as to complete those outer shells. Okay. Did that go like this? Or are you just stunned from taking an exam? That could be. So the ionic bond is purely electrostatic. Once you've transferred the electrons and you know what the charge is, you can actually calculate the force between them using Coulomb's law. We're not going to do that, but it can be done. And this has to be a complete transfer of electrons for the ionic bond to occur. Although, I will throw this fly into the ointment. Every bond has ionic and covalent character. Just the more ionic it has, the character it has, the further apart that metal and nonmetal are from one another. So if you form a bond between lithium and fluorine, then the ionic character is almost 100%. Not quite, but almost. So there's still some sharing character in there, covalent character. But if you get them closer, like maybe, I don't know, magnesium and phosphorus, a little closer, they'll have more covalent character and less ionic character. Okay, I mentioned this already. Covalent bonding is formed by sharing electrons. So when we write, some books will, well, let's see, let me pick a different one. How about carbon dioxide? Right, if you have 2 oxygens bound to that carbon, carbon has 4 electrons in its outer shell. Notice where it is on the chart. Count from the left. Lithium, beryllium, boron, carbon has 4 electrons in its outer shell. Right? Its position on the table tells you that. 4 electrons. Right? 4 electrons here. So in order for it to be happy, in order to look like neon, it needs 4 more electrons. So it gets those from oxygen. Right? How many does oxygen have? Well, it has 6 electrons in its outer shell. 6 electrons. So it only needs 2 electrons. And it has to share them because carbon and oxygen are both nonmetals. So this carbon picks up 2 electrons from that side, 2 electrons from this side, right, and gives it 8 in the bonding. Whereas oxygen only needs 2. So it picks up 2 electrons from carbon and 2 electrons from carbon on this side, and it thinks it has 8 in that share. And we represent those bonds since there are, let's see, since you've got 4 electrons shared from these 2 oxygens, 2 each, right? So you have 2 of these electrons here, 2 of these electrons here, and carbon has like 4 electrons. Then you put 2 of those together and 2 of these together, 2 of those together and 2 of those together, and you form 2 bonds. 2 electrons means 1 bond. So that's why we often write carbon dioxide like this. That's a double bond. 2 electrons, 2 electrons, double bond. Is this new? Or have you seen this before? No? Okay. Everybody's trying to look like a noble gas. Keeping up with the Joneses. Okay, this is what I mentioned earlier. Most bonds are not 100% ionic or 100% covalent. Even the covalent bonds have some ionic character. And we're going to look at that eventually as polarity, bond polarity. In other words, if one atom in the group has a stronger attraction, one atom in the bond has a stronger attraction for electrons, but not enough to completely remove them, then they tend to spend more of their time around that atom, and that gives it a slight negative charge. Since they're drawn away from the other one, it gives it a slight positive charge, and you develop a polar bond. It's still covalent, but it does have some ionic character. All right, it's important. I didn't mention this earlier. I was talking about valence electrons. All electrons that belong to an atom don't participate in bonding. Only the valence electrons. You remember the concept of valence electrons? I think we introduced that when we were doing electronic structures. So let's go back to oxygen. Right? As 8 electrons, 8 protons and 8 electrons. So what would its electronic structure be? Get me started. What's the first orbital? We did do this, didn't we? Does that look familiar? 1s? Okay. 2s, 2p, that's probably all we need. So how many electrons can be in an s orbital? Just 2, right? And that one's 2. So we've used up 4 of them. We've got 4 more to go. So we put those 4 there. Okay. The valence electrons are the ones that all have the same principal quantum number, that number right there. So these 6 are valence electrons. They're the ones that can participate in a bond, in any kind of bonding. Anything else below that, in this case, it's just those 2. These are core electrons. And they don't participate in bonding. Okay. Now, if we wanted to complete this outer orbital, right? Those are full. That's full. We got 4 here. How many more do I need in a p orbital? 2. Right. So I need 2 electrons from somewhere. That's why oxygen needed 2 electrons from the carbon. And it used 2 of these electrons in the bonding. But by receiving those 2 electrons, how many now do we have in the valence shell? If you put 2 more here, plus 2, you have 8. That's the octet that you may hear about again later. Now, the octet rule, which means a complete valence shell, only works for the second and the third period. Right? The one starting with lithium, the one starting with sodium. Because what happens when you get down to the 4th period? Potassium, calcium. Then you got d orbitals, right? And how many electrons does the d orbital can it hold? Right. There are 5 subshells, but 2 electrons each. So 10 electrons. That's why there are 10 elements across there. But on your way across, right, if you fill those up, it's going to take more than 8. So the octet really only works well for the second and the third period because there's 1, 2, 3, 4, 5, 6, 7, 8 across there. Right? It skips over that gap in the middle. And what about hydrogen? Can it have an octet? No. It follows the duet rule. All it needs is 1 electron or give up 1 electron. That's all it has access to. It has no core electrons. It only has valence. That 1s orbital is all hydrogen has to work with it. Okay. So this octet rule, I think we're going to encounter it again with Lewis dot structures. Lewis dot structures are based upon the octet rule, and they help us visualize bonding. Okay, so we're going to get there, I think. All right, ionic bond is formed between with a transfer of 1 or more electrons from an atom to another. There are your valence electrons. So maybe I didn't talk about this earlier, right? I just did. The valence shells are those that have the same principal quantum number right here. So if we had something like, I don't know, phosphorus with 15. Okay, we have 1s2, 2s2, 2p6, 3s2, and 3p, 2, 4, 10, 12, 3. So this would be the valence shell right here. And how many more does it need? It needs 3. It's 3 electrons. Okay, and you can count from phosphorus, sulfur's 1, chlorine's 2, argon's 3. 3 steps over, 3 electrons gives you a noble gas configuration, and that completes the octet for phosphorus. All right, we are going to do that. All right, so let's talk about Lewis. GN is initials, GN Lewis. Was working with bonding, and he was trying to figure out a simple way to show electrons around atoms so that he could imply a certain number of bonds around a given atom. And he hit upon this octet business, right? So what he did was he took, at least for the second and the third period, it worked really well. And you can form an octet by using dots around the symbol. We're going to do that in a second. These are examples. Notice that everybody in the first column has 1 dot. They've only got 1 valence electron. The s orbital with 1 electron only. So that's all the valence electrons they have. Lithium, sodium, potassium, only 1. The next door neighbor has a 1s, but it has 2 electrons in it. Not a 1s, it has an s orbital. Hydrogen's 1s. Lithium, beryllium would be a 2s, 2. Magnesium would be a 3s2, calcium would be a 4s2. And they stop at calcium. Notice they stop at calcium there because at calcium, actually these work okay too. At calcium, you jump over, you're getting into transition metals. So those don't work. But the second and third period over here, aluminum and boron have 3 valence electrons, right? A S with 2 electrons and a P with only 1 electron. Okay, and that's the way Lewis represented the elements and their valence electrons. So oxygen, remember, has 6. Right? The best way to place them is to put 1, 2, 3, 4, and then start pairing them up. 5, 6. So there's 6 electrons around here, and you can see at a glance, in order to complete the octet for this oxygen, you need 1 here and you need 1 there. So you need 2 electrons to complete the octet. So where does it get them? Well, it can get them both from 1 atom, like carbon, or it can get them 1 from one and 1 from another, like water. I can put a hydrogen out here and a hydrogen here. There's the 1 electron from the hydrogen. There's the other electron from the hydrogen. Now you got a bond. 2 bonds, actually. So that was G.N. Lewis's solution to the problem. So he could visualize this bonding. Now, it wasn't perfect, but it was a step in the right direction. All right. So let's determine the number of valence electrons in each of one of these. Start with calcium. Where do we begin with calcium? How many electrons does it have as a neutral atom? Calcium has 20. Has 20 electrons, but we could do it like this. 2, 4, 10, 2, let's see, 10, 18, yeah, and 20, 4s2, right? So there's your valence shell. But we don't have to, that's the hard way to do it. The easy way to do it is to look at where it is in the periodic table, right? Calcium is in the 4th period, right? It's filling s orbitals. Those 2 columns are s orbital columns, alkaline metals, alkaline earths. So calcium is in the 4th period. It's filling the 4s orbital, and it only has 2 electrons. So we just put 1 here and 1 here. That's calcium. There it is. 2 valence electrons, 4s2. Okay, I'll leave that up there. How about selenium? Where's selenium? You know where it is? You find it? That's one of the ones I think I wanted you to memorize. It's right under sulfur and under oxygen. It's a chalcogen. So it's going to have the same number of valence electrons as oxygen, sulfur, and tellurium. That's why they have similar chemical behavior, because they have the same number of valence electrons in similar orbitals. That's why they behave the same way. Okay, selenium. If we start from the left, we say potassium and calcium are 4s1 and 2. Right? So it has 4s2. When we get to the transition metals, now we're into 3D, right? And it goes all the way across, 3D 1 through 10. Right? So we have 3D 10. Now we're back to 4s. Gallium, germanium, arsenic, selenium. That's 4. Right? So we have 4p4. Now, by definition, this and this are the valence shell. Right? Has 6 electrons. 1, 2, 3, 4, 5, 6. Now, I know I mentioned that the d orbitals kind of interfere with things, but this is a starting point. These are valence electrons for the starting point. What we're going to find out is when selenium actually bonds with a number of different atoms, it can exceed the octet. Right? Instead of just having one electron here and one electron there to make it complete, maybe it's got an atom here, an atom here. It's got a couple of atoms. Right? So how does it do that? Well, I'm kind of giving you a tease for the future. It uses those d orbitals. Right? It has those extra d orbitals. It can exceed the octet by using the d orbitals. So we'll let that lie for now. But as far as drawing the Lewis dot structure, we're working with the octet. And in selenium's case, we're working with 4s2 and 4p4. And you can see that on the periodic table because it's in the fourth period. Okay. How about carbon? Carbon should be easy. Right? What is it? 6? Yeah, it has six electrons. So it's we could say 1s2, 2s2, 2p2. Yep. So it has these. It has 4. 2s2, 2p2 are its valence electrons, and it has 4 of them. So we put one there, one there, one there, there. And you can also see from where it is in the periodic table, from the left, lithium, beryllium, boron, carbon. That's 4 steps over from the left. It has 4 valence electrons. That's why some charts still have that Roman numeral, right? 1A, 2A, 3A, 4A. And those are valence electrons, those Roman numerals. Okay, think you can do that? Not without practice. Right? Lots of practice. That's why I give you that review document. It'll give you practice. All right. Now that review document includes chapters 4, 5, and 6. So if you start working on it now, you may run into some problems that we haven't covered yet. So if you do, just skip over them and come back to them. All right. Generalizations about valence electrons. I mentioned this one a little bit earlier. If an element occurs in the same group, it's going to have the same number of valence electrons in it. That's why it behaves similarly. Its chemical nature is similar. Now, Mendeleev didn't realize that. He didn't know this. He just knew that they had similar characters, and that's how he grouped them. But now we know why they behave similarly, because they have the same number of valence electrons in similar type orbitals. Right? They're not exactly the same. Right? Those electrons in sulfur are in a 3s3p, whereas for oxygen they're in a 2s2p. Right? They shrunk down. They're smaller. Right? But they do behave similarly. The number of valence electrons for representative elements is the same as the Roman numeral. Right? I just mentioned that one. So for the first 2 on the left and the 6 on the right, the valence shells correspond, the valence number of valence electrons corresponds to the Roman numeral. Right? When I had you fill this extra credit out, we use the newer system. It's just 1 from 18 from left to right. But those Roman numerals had their place. They were useful. And the reason they were used originally was for that. It would tell you the valence electrons. Notice that in the transition metals, those have a B suffix. Right? The A's, Roman numerals, do tell you the number of valence electrons. But the transition metals kind of get jumbled up. Right? So we're not going to just ignore the Roman numerals for the transition metals. They don't make any sense. At least not to me, anyway. The maximum number of valence electrons for any element is 8. And for now, that's good enough. We will tend to ignore the transition metals as long as we skip over them and stay in the representative region. First two, last six. Then that rule tends to hold. It's just, it gets a little squirrely as you get down below aluminum, silicon, phosphorus, sulfur, and chlorine. Get down below there, then it starts to not necessarily fall apart, but it tends to balloon. All right, how about the Lewis symbols for each one of these? We did these once before, right? Oxygen. So we look over there, see oxygen. If you don't want to look for the Roman numerals, just count from the left. 1, 2, 3, 4, 5, 6 oxygen. 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. And phosphorus. Come on. There we go. Phosphorus. Right, we count over from the left. It's 5. 1, 2, 3, 4, 5. So that's phosphorus. How about fluorine? Fluorine is 7 from the left. It has 7 valence electrons. That's fluorine. Now we're going to use this method in a minute to predict the number of bonds between any two elements. All right. Octet rule, I mentioned that already. If you have 8 dots or 8 electrons from any source, either complete transfer or sharing electrons, you have an octet. And that's what they're aiming at. They want to look like noble gases. All right. So terminology. When an ionic bond forms and you transfer electrons from one place to another, you create an imbalance. You create a positive ion where the electron used to be and a negative ion where the electron ends up. And those have names. The positive ion is called a cation, right? Like sodium or calcium or aluminum. Those are cations. Anions are just the other way. They're negative ions, like chlorine or oxygen or nitrogen. And the way that these are formed, just to hammer this point home, the way these ions are formed, positive or negative, is by transfer of electrons only. Right? The rule is don't touch the protons. This is chemistry. It's not physics. It's not nuclear physics. Right? In nuclear physics, you can touch the protons all you want. Right? You can touch the neutrons too. But in chemistry, it's all about the electrons. If you add electrons to a neutral atom, you're adding an extra negative charge. You make an anion. If you subtract an electron, you still got the protons in there, the positive charge, the nuclear charge. So if you remove an electron, you have an imbalance of 1 proton. Move 2, imbalance of 2 protons. That makes the cations. All right. And this is the author's idea of, it does illustrate one point. Aside from the fact that those electrons are not actually in those orbitals, right? It looks like they are, but we know now that they're not. But one thing I'll call your attention to is the size. Right? A cation, when it loses an electron, it vacates part of an orbital, right? And a cation will shrink from its neutral atom. It'll shrink by losing that electron. Okay? Whereas the anion, when you add an electron to it, it'll get bigger. And that's a generalization that works every time. So the chlorine in the bottom, chlorine ion got bigger and the sodium ion got smaller. Okay. Chemical symbol for each of the following ions. The ion formed when a potassium atom loses one electron. Potassium loses an electron. Now it has an excess of one positive charge. Right? And that makes sense. It's an alkaline metal. And all of those guys are positive when they form ions. How about sulfur? When it gains 2 electrons. Right? Now it has an imbalance of 2 negatives. There you go. Well, you form ions, cations, and anions when electrons are transferred. All 3 of those. Okay, atoms tend to gain or lose electrons until they have obtained an electron configuration that's the same as that of a noble gas. All right, I've said that before, so I don't think I need to hammer that one anymore. If you want to know which noble gas they're trending toward, that's where the periodic table can be of major help. You just look, where is it on the periodic table? And say, all right, if it's a non-metal, it's probably going to gain electrons and shift toward the right, right? Gain electrons to the right. So the noble gas it's trending toward is at the far right. But if it's a metal, they tend to lose electrons. And that would back up to the left and then up to the next period. And that's where you find their noble gas. So sodium would back up to be neon, potassium would back up to be argon, calcium would back up to be argon by losing electrons. Whereas bromine would gain an electron and look like krypton. Or nitrogen might gain 3 electrons and look like neon. All right. And that we can demonstrate that with the electronic configuration, but the periodic table tells you all you need to know. If that's the question, the answer is easy. You just look at the periodic table and see, where is it starting? Which way is it going? Add electrons, subtract electrons, and work your way either to the right or to the left and back up. All right. The point we're making here is that if sodium could look like neon or argon, but which one's easier, right? Lose an electron from sodium, you only have to lose 1 electron to go to neon. Whereas if you want to add electrons for sodium to look like argon, you got to add 7 electrons. That's a difficult task in any chemical reaction. All right. So, right, we're gonna, hold on a second. Yeah, we're gonna learn how to name compounds. And one of the things you have to know is based on where the elements are in the periodic table, some of them will only convert to one type of ion. Right? Either a +1 for that first group, lithium, sodium, potassium, rubidium, cesium, francium, they're all +1s. Right? When they lose an electron. Whereas the second one, the alkaline earths, they want to lose 2 electrons. Okay? Boron, aluminum, gallium, right? Skip over the transition metals. Over to boron, aluminum, gallium, they want to lose 3 electrons. And back up to, aluminum would back up to neon by losing 3 electrons. And those are the only charges that they have. available to them. On the other hand, the halogens, fluorine, chlorine, bromine, iodine, astatine, they want to gain an electron and just move one step to the right and look like that noble gas. So they're all -1. And this is a -1 charge for transfer of electrons. Right? You're going to notice on your periodic table, let's see. Let me get my copy of the review document here. I want to be sure I'm not speaking out of turn. No, that doesn't have. Wait, that's the wrong one. Okay, I'll leave it. Where's my copy of the review document? I don't have one. Did you guys leave me one? Yeah, here we go. Need this one. Here's the answer to it. All right. Yeah, it does have a periodic table in the back. There you go. You'll notice that in these boxes, sometimes there are multiple charges down the right-hand side of each box. The one that we're referencing right now for any of these elements is the first one at the top. That represents the charge. These other possibilities are what's known as oxidation states, and we haven't got to that yet. So just look at the first one if you want to know the charge. Fluorine, chlorine, bromine, iodine, they all have -1 first charge at the top. Okay. Oxygen will have a -2, sulfur -2, selenium -2 first, and then nitrogen, phosphorus, all the nicogens have -3 at the top. That's where we're focused our attention. Okay. Now, why do I need to know that? Particularly for the metals, the alkaline metals, the alkaline earths, and the boron group. Boron, aluminum, gallium, actually indium also are -3, +3, excuse me, +3. The reason we need to know that is later on when we get to naming compounds. It's going to be important to know which ones have fixed charges, which ones have variable charges. Now, the variable charges usually come from the transition metals. They can have a host of different charges depending on what compound they're in. Along with some of those extras like tin, antimony, lead, bismuth. Those guys right in there, they can have multiple charges too, but we'll get into that later. But for now, the sodium, our examples here, sodium in the alkaline metals, magnesium in the alkaline earths, and aluminum in the boron group, they have those fixed charges. And they have those Roman numeral group numbers associated with them because that's where the electrons are coming from. Nonmetals, on the other hand, like fluorine's group, typically has -1 charge. When you're trying to form a compound with these metals and nonmetals, that's the charge they assume. Oxygen tends to be a 2-. All the chalcogens tend to be a 2-. The nicogens tend to be a 3-. Okay, these are important facts to remember. The carbon group can go either way, right? Because it's 4, right? You could add 4 or subtract 4 and end up with a noble gas configuration. So carbon is a little more, and members of the carbon group are a little more flexible in that respect. Okay. The concept of an isoelectronics series. If we write out the electronic configuration for atoms, ions, and we find 2 or more that have exactly the same configuration, those are said to be isoelectronic. Iso means same electronic species, right? You ever play with as a kid, play with those little roly-polies that they crawl along the ground? You touch them and they go roll into a ball. Those are called isopods. Pod means foot. They all have the same foot. They have a whole bunch of the same feet. That's what iso means, same. So they have the same electronic configuration. And there's an example there. The nitrogen ion, the oxygen ion, fluorine ion, sodium ion, magnesium ion, aluminum ion, they all have the same configuration as neon. They left neon out, right? But neon would have exactly the same configuration, right? 10 electrons. Okay. That's no big deal. But they can't be all neutral though, right? The only one that can be neutral and have that configuration is the noble gas. Let's see. 115. Okay. I think we're doing okay. Choose an alkaline metal, an alkaline earth, a noble gas, and a halogen so that they constitute an isoelectronic series when the metals have and halogens are written as their most stable ions. All right. The easiest way to do that is if it says, okay, we get to have a noble gas in there. So you pick a noble gas. Let's pick, I don't know. Let's pick krypton. How about krypton? Look on the periodic table. Which one is going to have the same configuration as krypton? The easiest one is just to move one to the left and make a bromine ion, right, where we add an electron. It looks like krypton. Or selenium. Add 2 electrons. It looks like krypton. If we drop down and move over to the left, we find rubidium. Rubidium with a +1 charge is going to look like krypton. Or right next to it, strontium. It's going to look like krypton. You can get that information from the periodic table. We don't have to write the configuration out, right? Unless it's a question on a test, of course. All right, so they used argon. Add 1 to chlorine and you get argon configuration. Subtract 1 from potassium, you get argon. Subtract 2 from potassium. I think I went overboard because it only said alkaline metal, alkaline earth, and halogen. Right. That was okay. That's okay. I did skip over. I went over into the chalcogens. That's where I messed up. Right. The electronic configuration for each species is going to be the same as the noble gas. It's going to be like krypton. Right. Can we do? Yeah, let's do krypton. It has 36. You want to do the abbreviated form? Let's start at argon with 18. All right. What's beyond argon? We come down to 4s. We come down to 4s2. And then we have a go across to 4p. 4p6. Right. That's krypton. Right. You remember that easy trick. Right. You start off with this core, and then you just add that to it. Just say start from argon, then you wrap it around, and you go back to potassium. All right, it's in the 4th period, so we know it's 4s2, potassium and calcium, and then we move across. Well, actually, what we need is 3d10 in here. Right, I left that out because we're crossing over the transition metals. So we do need that one. 4s2, 3d10, 4p6. All right. Now the number of protons are going to be different for each one. Right? We can't change the number of protons. So whatever that happens to be, let's see. Krypton's going to be, well, 36. And then bromine's going to be 35. Selenium's going to be 34. Then rubidium's going to be 37. And strontium's going to be 38. So it has a different number of protons. That's why they have charges. They got the same electronic configuration, but in order to get there, we had to gain one here, gain two there, lose one there, and lose two there to give you that imbalance. Let's see. What's the electronic configuration of magnesium ion? If somebody asks you that, what's the most stable ion for magnesium? Look where it is. Alkaline earth. Right. It has a 2+ charge. Right? Okay. So how many protons did it start with? How many electrons did it start with? 12. But now it only has 10 electrons because we have an excess of 2 protons. So we write the configuration: 1s2, 2s2, 2p6. That's 10. That's 10. That's it. That's its configuration, which should be that one. All right. So formation of, I mentioned this earlier, when we form an ionic compound, it's a metal donates an electron because they're the ones that go positive, and the nonmetal gains the electron. Right? You can do that with most metals and nonmetals, as long as they're not too close to each other along that line. And the metal is going to form the positive charge. The nonmetal is going to form the negative charge species, anion, cation plus anion. So the Lewis structure takes advantage of that. The Lewis dot notation to start forming bonds between elements. And the end game is trying to make noble gas configuration. Right? This example where sodium and chlorine are, we know sodium only has 1 because it's in the first group. Chlorine has 7 because it's in the halogen group. And we transfer 1 electron from sodium to chlorine, and now we have a cation and an anion. And sodium looks like it doesn't have an octet, but it does look like neon. Whereas chlorine has a complete octet, and it looks like argon. And then the electrostatic attraction pulls them together, and you have a bond. Sodium and oxygen, we can do the same thing. Only we need 2 sodiums, right? 1 sodium contributes an electron, makes a positive single charge cation. The other sodium does the same thing. By donating those 2 electrons, we take the 6 valence electrons in oxygen. Now oxygen has 8. It has its octet. And we show that around there, it has the complete octet. And since we added 2 electrons to it, now it has an imbalance of a 2- charge. So each of the sodiums will have a +1 charge each, and the oxygen will have a 2- charge. And that's the way you write ionic compounds. You look for their charge, and you say, how do I make it neutral? Right? If that's 2 minuses, I'm going to need 2 positives to make that neutral. Okay. Calcium chloride goes the other way. If calcium has a 2+ charge, chlorine only has 1- charge because it only needs 1 electron. Gets 1 chlorine gets an electron from calcium, and the other chlorine gets the other electron from calcium. Now calcium looks like argon, and chlorine looks like argon, electronically speaking. And again, we're just balancing charges to do that also. You can look at it 2 different ways. If you know what their most stable ions are, then you can write the compound, ionic compound, and write it in such a way that it balances the charges. Like calcium is an alkaline earth, those all have 2+ charges. Chlorine is a halogen, always has a -1 charge. So you need 2 chlorines to match the 2 positives from that 1 calcium. That's why calcium chloride is CaCl2. All right. I mentioned this in passing, but all ionic compounds are neutral, no net charge. So you ratio the charges with the number of atoms of each so that you get a neutral compound. Now, that is a compound because it is a combination of 2 or more different elements. But it's also referred to as a formula unit. And the reason it's called a formula unit is because of the way that ionic compounds tend to arrange themselves. They're always solids. And sodium chloride is a good example, right? If you ever spilled table salt on the table and looked at it with a magnifying glass? Nobody in this class ever did that. What you'll see is a cube. Every tiny little cubes, right? If you have coarse ground rock salt, it'll have big cubes. And if you have shaker salt that you're going to put on your eggs, then it'll have tiny cubes. But they're always cubes. And the reason for that is this cation is surrounded by anions. And there's one in front, there's one in back. So it's 3 dimensions. But each one of these chlorides is surrounded by a cation. And that goes on and on and on and on forever. What this formula represents is the simplest whole number ratio of cations to anions. If we wrote the actual formula for that cube, it would like be sodium 23 quadrillion sodiums and 23 quadrillion chlorides, right? So we're not going to do that. We reduce it to the simplest whole number ratio, 1 to 1. Right? So once you've got everything accounted for, you've got an equal charge, 1 sodium, 1 chloride, expanded as big as you want it. That's why we call this the formula unit. It is a compound, but this is the formula unit for an ionic compound. Because the true formula for the ionic compound depends on how big the crystal is. So we simplify. Calcium chloride would be similar. Only each calcium would have twice as many chlorides around it, then the chlorides would only have, you have 2 chlorides for every calcium. Okay, so we're going to learn how to write and name compounds. This is absolute essential skill that you need to have. And in order to master this skill, you have to know the symbols first. Right. I assume that you've been memorizing your symbols. If you haven't, now's a good time to really get on it good. So we typically, by convention, when we have a compound, we're going to start off with binary ionic. Compounds. That's our beginning. That's our model. That's where we start. Binary means 2. So you got one type of cation and one type of anion. And we bring them together in an ion with ionic bonds. So binary could be like that, or it could be like this, or it could be like this. Right? Binary, 2 elements. Ionic. And when we write the compound, we always put the cation first, and then the anion, by convention. And we don't show the charges. Now you can, when you're trying to balance it, sure, you can write the charges in there, right? Just to be sure you have it balanced, right? 2 plus and 1 minus, right? That's balanced. 1 plus and 2 minus. Okay, that's balanced. But when you represent the compound say a formula of any kind, you just write the formula. You don't put the charges in. Charges are understood. Okay. Subscripts, of course. Remember when I showed you the these different positions around the symbol? Right, subscripts down here, that means how many of them are there. So if we wrote a formula for this compound where we have sodium ions and phosphorus, let's see, phosphorus would be from left, 1, 2, 1, 2, 3. It needs 3 electrons to look like argon. So it's going to be a P 3 minus. We're going to add 3 electrons to make phosphorus look like argon. Now, how do we balance that out? Well, that's 3 minus on this one. So we need 3 of these times that plus 1 to balance those 3 minuses. So Na3P would be the formula for that compound. Okay, we got some more examples. Barium, and is that right? Barium 2 plus, where's barium? That's an alkaline earth, second column, almost to the bottom. So it is, yeah, a 2 plus charge. And with chlorine or chloride, right? It's a halogen, so it's -1 charge. Well, we need a 2 here. So BaCl2 would be the formula for that one. There we go. How about Fe3 plus and O2 minus? Fe3 plus and O2 minus. Now with this compound, we're getting into the transition metals. And those metals can have various charges. Like iron typically has either a +2 or a +3 charge. There are others in there that only have 1 charge. Like zinc only has a +2. Yeah, zinc is a +2. Cadmium is a +2. Silver is a +1. Those are the only ones in there in the transition metals that have fixed charges. Right, so we would treat them when we learn how to name compounds. We treat them the same as we would the other fixed metal charges. But iron could be 2 plus. In this case, it's 3 plus, and we're told that. So all we have to do is say, how do you balance an odd and an even? Go back to your math class. Your instructor ever talk about cross multiplication? You got to find the least common denominator. Bring the 2 over here and the 3 over here. 3 times 2 minus is 6 minus. 2 times 3 plus is 6 plus. Right? 0 charge. Okay, so Fe2O3 would be the formula for those 2 ions. Okay? Let's move over here. How about Pb? What's Pb? I'm sorry? Lead. Yep. And oxygen, 2 minus. So how do we get those to balance? Yeah. 2 times 2 minus is a 4 minus, balance is a 4 plus. We're good to go. All right. Now we need to know how to write these compounds. If you're confronted with a word problem that gives you the name of a compound, you got to be able to take the name and write the compound from it in order to complete the reaction in an equation. Right, we're going to get there, but you need to know how to do this. First the symbols, than the accepted charges or the charges that are given for iron in that case, because it could be 2+ or 3+. So they have to tell you what it is. Lead could be a +2 or a +4, right? But they told us what it is. What's the correct formula for the combination of aluminum and chlorine? Actually, we call it chloride, the chloride ion versus the aluminum ion. Cation, anion. We need 3 chlorines, don't we? All right, so wouldn't C be the best one? Yeah. That way you get 3 minuses from the chlorine, you get 3+ from that one aluminum, and they balance. Everything's neutral now. All right, I mentioned this earlier when we talked about the cubes of little sodium chloride table salt. These solid ionic compounds consist of an array of cations and anions in the mix, right? And depending on what that ratio is, you get a different, and how they're put together, you get different crystal shapes, right? Has anybody ever seen, let's see, what is calcium chloride crystal? A natural, I think they call it calcite. It's a rhomboid, right? It's like a cube, and you hold the bottom fixed, and you take the top and you go, you push it over. Actually, you push it this way and that way. It's an oblique rhomboid. And the interesting thing about it is, if you ever get the chance to use one of those crystals, put it down on a piece of paper that's got writing on it, and it splits the words into 2, and you can see 2 lines through that crystal. But the shape depends upon, well, several things, but initially it depends upon this ratio of cations to anions. And then there are other factors that enter in, but the ionic solids are an array of sodium, of cations and anions. Okay, so there's your cube for sodium chloride, and notice that the chlorides are bigger than the sodium. Right? They're in the same period, but the chloride has acquired an electron, and sodium has given up an electron. So it shrank, chloride got bigger. So that's the way they fit together in that cubic lattice. And the formula unit is just what I described earlier. It's the simplest whole number ratio of cations to anions in the crystal. All right. What term is used to refer to the smallest whole number? Oh, the formula unit. Sometimes, especially on old bottles of chemicals, if you run across an old bottle, sometimes it'll they'll have the formula of the compound in the bottle, and then underneath it they'll have FW and a number. FW means formula weight, right? It's how much in grams a mole of that formula weighs. Okay, we did molar mass already, didn't we? Yeah, calculating molar mass. We didn't do that. Okay, we are going to do that. All right, so these are fixed charges, and we need to know those fixed charges for metals. Right, all the alkaline metals are +1. All the alkaline earths are +2. Aluminum and gallium. I don't know why they left boron out of there, because it's a +3. Probably because it's in the non-metal side, so that they left it out. But aluminum and gallium for sure are 3+ charge, and zinc and cadmium are 2+ charge only, and silver is 1+ charge only. Those are the fixed charge elements that we're interested in. Fixed charge metals. All right. So in addition to this binary ionic compounds, you can have binary covalent compounds. if they're formed from two different elements and they're both nonmetals, then you're going to get the covalent compounds. And we're going to use the binary ionic compounds as our starting point for naming compounds. Right. So we're going to start with type 1 compound for naming purposes. And underlying all of these rules, which are created by a subcommittee of that organization, the International Union of Pure and Applied Chemists. They have a subcommittee that does nothing but name compounds. And they develop these rules with two premises. One is that they're, let's see, I want to say unique, but there's a better word than that. They're unambiguous. In other words, if you have a name of a compound, there's only one formula that will satisfy that name. They're unambiguous. And they're non-redundant. So if you write the formula a certain way, based on its unambiguity, then you don't have to add information to it because the information's already there. You don't say it twice. I'll give you an example. I'll give you examples in a minute. Type 1 compounds. Okay. Type 1 compounds are metal with a non-metal. Okay. I better do this so you don't think that's a nitrogen. Metal, non-metal. The characteristic of this type 1 is that the metal has fixed charge. Fixed charge for the metal. And that means it's one of those that we showed you in the previous slide. Either the alkali metals, alkaline earths, or aluminum, gallium, indium, or zinc, cadmium, silver. They have a fixed charge. Since they have a fixed charge, you don't have to say what the charge is. You know what the charge is. And you combine, as the binary we did before, you combine the metal, the cation. You just say that the cation is the element name. That's it. You don't have to change it. So if sodium's in there, you just say sodium, or calcium, or aluminum. You don't have to change it. That's the first part of the name. And then the second part of the name is the anion. And if it's an element, you change the ending to IDE. So if it's chlorine, you say chloride. If it's fluorine, you say fluoride. If it's oxygen, you say oxide. If it's phosphorus, you say phosphide. Okay, that's the way you name the compounds. Let's see, they're going to give us some examples. Yeah. Well, the stem and the extension. Those are a bunch of examples. Sulfide, nitride, I didn't mention that one. Hydride, that's a good one. So if hydrogen has a negative charge, sometimes it does. Usually it occurs as positive, like it loses an electron and becomes what's left over, a proton. But if it acquires a negative ion, how would hydrogen acquire an electron in a chemical reaction and make a compound? Where would that electron have to come from? More than likely, came from a metal. Metals like to give up their electrons. So if we have sodium and hydrogen, right? Sodium has the positive charge, hydrogen has the negative charge. And in that case, we would say sodium hydride. Okay. All right. Examples: potassium +1, chlorine is a -1, just 1 and 1. Potassium chloride. Magnesium bromide. Now, why don't we use a prefix and say how many bromines there are? Because that would be redundant. We know that magnesium has a fixed charge, and bromine has a fixed charge. The only way to get those two to work together is to put 2 there. So you don't have to say dibromine, dibromide. Right? That would be redundant. It's unambiguous just to say magnesium bromide, because we know magnesium is that, and we know bromine has to balance. Okay. Calcium oxide. Right. That works too. That's a type 1 compound. And it's between a metal and a non-metal, and the metal has fixed charge. Never guess what the next one is. Type 2. It's also a metal and a non-metal. The difference is variable charge. That doesn't mean that in the compound that the charge just flips around, right? Once the compounds form, the charge is fixed for the metal. But the metal coming in could acquire one of 2 or more different charges. That's what we mean by variable. And iron was our previous example. It could be a +2 or a +3 in any compound. But once it's in the compound, and our example was a +3, once it's in the compound, then that's its charge. But we need an unambiguous way of designating that charge when we name the compound. Right? So that previous example was this, wasn't it? Wasn't that it? Fe2O3. So we start from here and we say iron because that's the cation, and then we need oxide as part of the name. But because iron can have different charges, we want to be able to take this name and write that compound without making any mistakes. So we need to say in the name what is the charge on the metal, and we do it with a Roman numeral. Iron 3 oxide is the way you say it. All right. And we know from this name that iron is going to have a 3+ charge, and oxygen's always a 2-. So now we can write the compound, 2 here and 3 there. And we don't say how many there are. We don't say diiron trioxide. That would be redundant. Okay. Now, most of the variable charge elements are transition metals, right? Except for zinc, cadmium, and silver. The rest of them have multiple possible charges. So they would fit into the type 2 naming convention. Some others: tin, antimony, lead, bismuth, tellurium, polonium. Those also would fit in here because they have multiple charges possible. But we still use this naming convention, the metal and IDE, only now we have to put the charge in. That's a type 2 compound. Right? CuBr. Right? We know if we give them the formula CuBr that copper can only have a +1 charge. Now, copper can have, depending on the compound, a +1 or a +2 charge. But in this case, it's a +1 because bromine is a -1. So that's how we calculate what's the charge on copper, because we've only got 1 bromine, 1 copper. If you're given that formula, then you know that the charges have to balance, and copper must be a +1. It can't be anything else. So we say copper 1 bromide. FeS. Sulfur is a member of the oxygen group, the chalcogens. It's a 2- charge. So the iron has to be a 2+ charge because there's 1 and 1. PbO2, that's lead oxide. But the lead must be a 4+ because oxygen is a chalcogen. It's a 2-. There are 2 of them, so that's 4 minuses. That one lead must carry a +4 charge in order to balance. And that's why it has that Roman numeral 4. All right. I guess we can stop here. I think, I didn't hand out the polyatomic chart, did I? Did I give you a chart of polyatomic ions? I did. Oh, yeah. No, with the here with 50 ways to name your compound. Yeah, it's in there. So because this is really small print, right? And you're going to have to look at that printed chart to actually make sense of it. What I will point out is that polyatomic list is sorted. The left-hand list is exactly the same as the right-hand list. Only one on the right is sorted by formula. One on the left is sorted by name. So if you need to find the formula from the name, you use the left-hand side. If you need to find the name from the formula, use the right-hand side. And these, you don't have to memorize these, but you do have to know how to use this chart, right? This chart will be available on the exam. Okay. So you can find these polyatomic ions. Now, I haven't defined what a polyatomic ion is yet, have I? Well, it's an ion, right? And polyatomic means there's more than one atom in that ion. And what that means is that the polyatomics have atoms that are bound together tightly in a covalent arrangement. They share electrons. But the whole unit carries a charge. Now, it's important to remember that the charge is distributed over the entire unit of all these atoms together. So it behaves as a single charged unit. All of these, except for one, are anions. They're negative ions. The only one that's positive is ammonium. So the reason I emphasize that point, that this charge is carried by the whole unit. We write it up here, but it doesn't belong to hydrogen. It belongs to the whole group. The reason I tell you that is because when you start to put it into a compound, if you need more than one of them, then you've got to use a parentheses and a subscript for the whole unit. You can't change the subscript of a polyatomic. If you need, if you need 2 positive charges to balance something else, then you do like that, right? Say you have sulfate, which is another polyatomic with a 2- charge. Well, this is only a 1+, so you need 2 of them to balance that. We're using the same type of convention that we would here. Balance the charges. Only now we're using polyatomic ions. Okay, you can combine metals and polyatomic anions, or you can combine this one cation with different anions. Doesn't have to be polyatomics. It can be anything. It can be chlorine for all that matter. If that were the case, it'd be 1 ammonium and 1 chloride. That would be it. Just 1 and 1. All right, here's some examples. Hydroxide is a polyatomic ion, OH-, combined with sodium. And one thing about the polyatomic ions, you don't have to modify their names. Their names are given. They're chiseled in stone on that page. So once you see that name, that's the name you put into the compound name. Sodium hydroxide. That's it. Hydroxide is a -1, sodium is a +1. That's all you have to say. because sodium is a fixed charge. It's a type 1. Magnesium nitrate. Magnesium is a +2 charge. Nitrate is a polyatomic with a 1- charge. So you use a parentheses, gives you 2 of them. And that gives you 2 negatives with 1 magnesium at a 2+. You got a neutral compound. And I just gave you this one, that last one. Let's see. There's another list in table 4.3 in the 7th edition of your textbook, I think. But I'm going to work off of this list. Okay. That's how the polyatomics work. Here we go. Type 3. This is the last one we're interested in. I should have started over here. Put type 3s over here. Type 3 compounds are non-metal, non-metal. So where do they come from? Right-hand side of the table. Both elements in the binary compound come from the right-hand side, like carbon and nitrogen, carbon and oxygen, nitrogen and chlorine, or nitrogen and fluorine. Both non-metals. What we now, since they're 2 non-metals, they're sharing electrons. They don't form ions. Right? So we can't balance charges like we would with a type 1 or a type 2 to be unambiguous. In order to be unambiguous with a type 3 compound, you have to actually say how many of each atom is in the compound. And we use prefixes that are on the next slide, I think. Yeah. We use those Greek prefixes to tell us how many are in the compound. That's why that one, carbon and oxygen together, is carbon dioxide. We still use the ionic naming convention, right? The first one here, the second one here, change the ending to IDE. But now we put a prefix in there. And notice that we don't say monocarbon. Right? The cation side, it's not a cation, but the cation side never has a mono with it. We only start with di. Don't ask me why. It's just, maybe it just sounds better. But over here, if you have just one of something over here, then you say mono. Or if it's like, well, okay, let's take the really poisonous version. Carbon monoxide. That's CO. That's the one that results from incomplete combustion from poorly made or poorly maintained gas furnaces, or if you, I don't know, shut your garage door and turn on the car engine and off yourself with the exhaust. That's the culprit right there, carbon monoxide. But there's 1 oxygen and 1 carbon, right? So we say carbon monoxide. That's the compound right there. It's unambiguous, non-redundant. We don't say monocarbon, and we don't say monooxide either, because two O's together don't sound right. So we drop an O out of that and just say monoxide. Sounds better. So let's see, we got some examples. We do all the rules. Yeah, we did all the rules. So there's the carbon dioxide that I did before, SF6, right? First thing you want to do is say, are those both nonmetals? Right? If they're both nonmetals, then you go immediately to the type 3 convention. SF6. Sulfur, right? Just like before, sulfur, and the prefix for 6 is hexa. Fluoride. Okay. So it's is mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca for 10. That's why when you pull up to fill your tank with gas, what does it say on there? What are those numbers? What, 90, 97, 93? Octane rating. That comes from the name of the primary ingredient of gasoline, which is octane. Right? It's a hydrocarbon. It has 8 carbons. So the octa means 8. This means 6, sulfur hexafluoride. N2O4. Now we've got one where we need to say 2 nitrogens. So we say dinitrogen, tetra oxide. Actually, we drop the A. Tetroxide. You ever seen that the King Kong movie with Jeff Bridges in it? Remember that? The name of the company that was going to that island where the big ape was, it was called Tetrox. Anyway, that's the name for N2O4. How about this one that's not on there? How about, how would we name? I say, let me give you the name and you tell me the compound. Okay? Let me think of a good one. How about this one? Di, phosphorus, pentoxide. How's that? How would I write that? First of all, is it a type 3? Yeah, phosphorus and oxygen. They're both nonmetals. No idea? Phosphorus, you need 2 of them. Oxygen, you need 5 of them. There's the compound. Unambiguous, non-redundant. Now, I was going to give you an example of a redundancy. If we had magnesium chloride, right? Magnesium is a fixed charge, so it's type 1 compound. Magnesium, let me do fluoride, right? So this is a 2+, that's a 1-, so we need 2 of those, right? Let's name that one. But let's name it so that it's redundant. Magnesium 2 fluoride. That's redundant. We know magnesium only has a +2 charge. We don't have to say what the charge is. So we don't need that. That would be redundant. All right. So we got type 1, type 2, type 3 compounds. And there's a decision tree. All that decision tree tells you is when you're faced with either a name to write the compound or a compound to write the name, you look at it for metal, non-metal, or non-metal, non-metal. That's the first decision. Right? If it's got a metal in it, then it's either a 1 or a 2. You don't have to consider the 3. Right? That means you don't use mono, di, tri, tetra, that stuff. That's out. Then, if you have a metal, non-metal, then the second question is the metal a fixed charge? Does it come from the first 2 groups, the aluminum group, or zinc, cadmium, or silver? Right? If it does, it's a type 1. And you know how to name that one. Just balance the charges. If it doesn't, I mean, if it's not one of those, then it could have a multiple charge. And then if you're going to write the name from the compound, you deduce the charge on the metal based upon the balance of charge in the formula that you're given. And then you, in parentheses, you give us the charge on that metal. Now, of course, if you've got the name with charge built in, then you know it's a type 2, and you write the formula You write it out like this, and you put the charge here, right? 3 plus, and you know oxygen's 2 minus. Then you balance the charges, and that's the formula. So you go backwards and forwards. You go one way or the other. Name the compound or compound to name. You got to be able to do that. Because when we start writing chemical equations, if you don't know how to do that, then you're stuck. You can't do it. Polyatomic ions, on the other hand, are treated like, well, they're mostly anions. So they're going to have their given name. They're going to have a charge that you can find on the chart. Learn how to use that chart. And the only cation is a fixed charge. So anytime ammonium is involved, you're going to use type 1 convention, right? It only has that one charge. All right. Now the fun really begins. How do you name acids? First of all, we're going to find out what is an acid. And the rules still apply, unambiguous and non-redundant. Let's see. I'll erase the bottom part and leave the top part up there. We have a set of rules that we use for naming acids. And unfortunately, the committee, the IUPAC committee, had to deal with history, right? Naming conventions that had filtered through from the Middle Ages and alchemists. So they had to standardize naming of acids in such a way that it made sense and it didn't discard the historical names that had come down to us from the chemical magicians of the Middle Ages. So, in order to be an acid, the compound has to start with at least one hydrogen. Okay, you can have 2, 3. I've never seen 4. But it starts with hydrogen in the formula, and then something beyond it. Okay, it could be a single element, like your example there, Cl. Okay. Or it could be a polyatomic ion, like nitrate. Or we could have another polyatomic ion, right, sulfate. But it always starts with a hydrogen. And it starts, now you can have other hydrogens over here, but the ones that we're interested in that make it an acid are there. Okay, example, acetic acid. If you look in your polyatomic chart, that is the acetate polyatomic ion. And this is the one hydrogen that makes it acidic, right? Now, the other thing that's required for an acid is you put it in water. At this point, it's got to be aqueous. It has to be put in water. So each one of these would have aqueous behind it. This one, for example, HCl, if it's pure, it'll be a gas. And if it's like that, you would name it just the way we would hydrogen chloride, right? Just like a type 1 compound. Okay, put it in water, then we have to invoke acid naming rules. First rule, is there an oxygen? Is there an oxygen in this part of the molecule past the hydrogen? Right? If there's no oxygen, the name starts with hydro. So this one would be hydro. And then you look at the other part of the name from its non-acid form, chloride. Ions become X. So it's hydrochloric acid. If you put that in water, that's what you get. And we only say hydro when there's no oxygen there. Another example, with a polyatomic, this is hydrogen cyanide, right? If it's a gas. If we put it in water, right, there's no oxygen there, so we say hydro. And I becomes X, so it's hydrocyanic acid. Okay, that's the first rule. Look for the oxygen. If there's no oxygen, start it with hydro. If there is oxygen, you just drop the hydro and you go straight to this part of the molecule and say, what is that? Right. In this case, this is the nitrate polyatomic ion. So we take that nitrate, and in this case 8s become X. So we say nitric, let's see here. Now we say nitric, not hydro, but nitric acid. That's it. If there's oxygen, you just go to this part of the molecule. And of course, if it's got oxygen in it, that's going to be a polyatomic ion. There's no other option. This one would be sulfate. 8s become X, only we modify it just a little bit. Right? Sulfate. Sulfic doesn't sound right. So we say sulfuric. Acid. Okay. And that's the rule for, and it's either oxygen or not oxygen. What if we did something else? Say we used a different polyatomic here. Right? That would be hydrogen sulfite. Ites become us's. So this one would be sulfurous acid. Okay. All right. There are examples. There's your decision chart if you want to use one. Let's see. I wanted to, when you're looking at those polyatomic ions, some of them are in a series. Right? They're based upon similar structures and they follow a pattern, which makes it easier to memorize them if you ever want to. Chlorine and oxygen together are a good example. So if we start with ClO3 minus, that's the chlorate ion. If we add an oxygen to it, let's subtract an oxygen, ClO2. That's chloride ion. If we subtract another oxygen, we don't have any more endings, suffixes that will satisfy, so we have to use a prefix. So for this one, we say it's under the chloride. We say hypochlorite ion, right? Like hypodermic, underneath the skin. And then if we add an oxygen to it, we need a different prefix, which is per. So perchlorate ion. And this pattern is the same for all the halogens, halogen oxides, right? You can use bromine there, you can use iodine there. So this would be 3R03 minus would be bromate, bromide, hypobromite, perbromate. Right? So you can learn a whole bunch of them at once like that. Then when you make an acid out of it, you just add a hydrogen. With a 1 plus against a minus, you only need 1. So in this case, The chlorate would be chloric acid, right, without the charge. This would be chlorous acid. This would be hypochlorous acid. And this would be perchloric acid. Okay. Very, very strong and dangerous acid. I used to use it to digest plant material. Right? Drive off all the organic matter and leave the ash behind. Only if you take perchloric acid, if you really want a nice light show, take perchloric acid in one of these tall beakers and set it on a hot plate inside the fume hood and drop a nice big pat of butter in it. Okay. Then turn your hot plate on high, pull the sash down, and evacuate the building, because eventually it will blow and it'll knock out a wall at least. So the way to make it safe is we took our plant material and we added nitric acid, this concentrated nitric acid, to it first and let it sit overnight, pre-digestion. Then we added our perchloric acid on top of that and heated it, no problem. Okay. Potassium perchlorate. How would we write that? Right. Potassium is 1 plus, chlorate is 1 minus, right? So that's potassium chlorate. Put it in solution and concentrate it as you can get it, and then go around the lab and just dribble it, right, in spots. When it dries, it's a small enough spot. I mean, it's white powder, but you can't see it very easily. And your professor comes walking in and steps on one of them, and it goes pow under his feet. Right. All it takes is that pressure shock to set it off. It's just decomposing and producing oxygen that makes a gas. It's not dangerous, but it's fun. Okay, which of the following compounds is named incorrectly? How about KNO3? Is that potassium nitrate? What type of compound is it? Type 1, 2, or 3? Look at the metal. Right? It is a metal, right? So it's either a 1 or a 2. Right? Potassium, is it a fixed charge? Yeah, it's an alkaline metal. It's a fixed charge. So we only have to say potassium and the polyatomic ion nitrate. That's it. We're done. How about TiO2? Right? Is titanium a multiple charge possibility? Look where it is. Yeah, it's a transition metal, Ti. So what we need to know is what's the charge. So we deduce the charge from that. Oxygen is a 2 minus, correct? It's a chalcogen. So that means 4 minuses. That means this one has to be 4 plus. Right? That's wrong. Titanium 4 oxide is what it is. Right. How about SnOH4? When you see a parentheses around 2 or more atoms like that, you can be pretty sure it's a polyatomic. So you can look it up in your list. OH minus is the charge. 4 times 1 minus is 4 minus. So 10 SN should be a 4 plus, correct? So 10,4 hydroxide is correct. How about PBr5? What kind of compound is that? 1, 2, or 3? It's not a trick question. It's a type 3, non-metal, non-metal. Right? Phosphorus and bromine. They're all over there on the right-hand side. All right, so we need to name it according to that convention. Phosphorus is the first one in the group, so we don't say mono. We just say phosphorus. If we say phosphorus, there's at least one of them. And then pentabromide, because there are 5 of them. Penta's the prefix for 5. How about CaCrO4? All right, are we going to try to name those as calcium chromium oxide? No. CrO4. If you have an oxygen, this is not true for all of them, but if you have an oxygen and a couple of other elements in the formula, I'd suspect polyatomic and look to see if there is one. Right. CrO4 is chromate. That's a polyatomic. It has a -2 charge. So 1 calcium at +2, which is alkaline earth, and 1 chromium. Right. Calcium is fixed, so it's a type 1. And chromate, calcium chromate is all you have to say. All right. So the only one that's wrong is B. We mentioned polyatomic ions earlier. This is a more complete description in black and white. The polyatomic ions are covalently bound. In other words, the members of the polyatomic ion are sharing electrons in order to produce that stable unit. But the charge itself is distributed over the whole. That's why when you need more than one of them, you can't change the subscripts. You have to use a parentheses. Okay. I mentioned this one earlier. Let's see. I'm not going past. Okay, we're good. Most polyatomic ions have a negative charge. At least the ones in that list do. The only one in that list that has a positive charge is ammonium. We're going to encounter hydronium later, I think, when we actually are working with acids in chemical reactions. The hydronium ion is another polyatomic, but you don't have to worry about that one right now. For naming convention, ammonium is the only positive polyatomic that you need to deal with. Most of the ions contain oxygen atoms. That's true. Most of the polyatomics have oxygen except for cyanide and ammonium. Two of the negatively charged polyatomic ions, OH- and CN-, have names ending in IDE. The rest of them have names ending in ate and ite. That's a holdover from, that's one of those things that the IUPAC committee had to deal with. ATE is a suffix for a word that means contains oxygen. That's all it means. ATE means oxygen. So we had to say, all right, what if there's a different number of oxygens? Well, then they had to insert ite in there to say, all right, we lost one oxygen, so that's an ite. And then we had to add prefixes in some cases, like this list here. Ammonium ends in IUM, right? Remember, these polyatomic ion names are not changeable. Right? When they go into a compound name, they go in whole. No changes, just as is from the table. Some of them, we change the number of hydrogen ions. For instance, I need some more room here. How about over here? For example, this is the phosphate polyatomic ion. We add a hydrogen to it. Then this 1+ neutralizes one of those negatives, and now we have a 2- charge. But it is a polyatomic ion. Right? This is phosphate. And this polyatomic name is simply hydrogen phosphate. We can also say 2PO4. Now we're down to 1-. And this is dihydrogen phosphate. Okay. Another example, CO3, 2-. That's the carbonate responsible for the fizz in your pot. Carbonate. We add a hydrogen to that one. We reduce it by 1 charge. This is hydrogen carbonate. Now, older naming convention, you may see this on some older products or even in foodstuffs where they still cling to the ancient. This is often referred to as bicarbonate. Okay. So if you add a sodium on that one, right, a 1 plus and a 1 minus neutralizes it. This is sodium hydrogen carbonate is the proper name, but you may see it as sodium bicarbonate. Baking soda. Okay, baking soda. Okay, that's what that point was all about. When you add a hydrogen, you reduce the charge by 1 negative because hydrogen comes in as a positive. Okay, what's a polyatomic? We did that one to death. You still have to have a neutral compound. Right, so if you introduce a polyatomic, you need to know the charge on the polyatomic plus the charge on the metal, or with ammonium, the charge on the nonmetal that it's combined with, and that way you can balance the charges. All right, that's a repeat. How they get stuck in there. What's the correct chemical formula for a combination of ammonium and carbonate? Right, ammonium and carbonate. Right. Parentheses, 2 of those. 2 times a plus yields a 2 minus balance. Okay, so that would be C. Okay, this last slide I stuck in there. It's called, this is when you're naming compounds that have waters of hydration. I guess I need to define what is water of hydration. When a compound comes out of solution, say you add 2 solutions that are completely soluble and put them together and you form a solid, that's a precipitate, right? It drops out. Or if you take that compound, that precipitate, right, just out of the bottle, put it in water, and then you dry it down, right? You let the water evaporate, and then you stick the rest of it in the oven at 105 degrees Celsius, right? What's the boiling point of water? 100 degrees, right? So you put it in the oven at 105, and you drive off all the water you think, and you weigh the compound. And then you stick it back in the oven at 200 degrees. And lo and behold, the weight decreases again. But you're not losing any of the compound because it's ionic and you're not hot enough to vaporize it, right? Ionic compounds don't vaporize till you get up in the 1,000 degrees. So why did it lose weight? Well, the first time you dried it, you left behind some water in the crystal structure. It looked dry, but it wasn't. There was water embedded in the structure. And when you dried it at 200 degrees, you added enough energy to drive off even that water. Those waters are waters of hydration. And they typically occur with a fixed mole ratio of waters to the compound. So for instance, if we're talking about wallboard, right? Most houses, unless you live in a really old house that has lath and plaster, then the walls are going to have wallboard on them, gypsum board. Okay, that's made out of calcium sulfate, but it has 2 water molecules for every 1 formula unit. And when we write it like that, we put a dot right here in the middle of the line. That's calcium sulfate dihydrate. Okay, that's gypsum. You name this compound first, then you say how many waters are attached to it. Okay. One that I use in my general chemistry class for for a lab is copper sulfate, and it has 5 waters associated with it. Let's see, what's another one that people like to use? Epsom salt, right? You get a sprain, right? You put Epsom salt in hot water and you stick your foot in it, right? Epsom salt, magnesium sulfate with 7 waters. Okay, those are all waters of hydration. They're not part of this molecule, but they are associated with it, so tightly bound that it takes more energy than it would to boil water. It takes more energy to liberate it. Okay, and that's what this slide is about. Let's see. Right, you name the compound first, then you say how many waters there are with those Greek prefixes. Right. So this would be dihydrate, this would be pentahydrate, this would be heptahydrate. That's Epsom salt. Epsom salt makes a good laxative too. It's horrible taste. Right. If you ever have a colonoscopy and they give you a choice as to what you have to drink to clean yourself out before the procedure, don't go with the one that has salts in it. Right. They have 2 types. They have one that's what's that? Poly. I forget the name of it. It's a polymer of some kind, and it's a lot easier to handle. It'll clean you out. But I tried that salt one last time, and you have to drink a lot of it, right, to do the job. But it's horrible. So don't do the salt one. Do the other one. You can buy it off the shelf. Right. That's a good laxative. Greek prefixes are the same as we've learned before. So that's it. Zinc sulfate is the same as this one, 7 waters. All right, I think that's the last slide. We have questions. Do we want to do the questions?
We've done a lot.
Huh?
We've done a lot of questions.
Yeah, I think there are 2 concept questions this case, aren't there? Yeah, 2 concept questions. So after placing a soft, lustrous, and malleable material in a container of yellowish gas. So what does soft, lustrous, and malleable material speak to? It's a metal. Right. That's a metal. And you put it in a container with a yellowish gas. It's probably a non-metal. Right. There's only one liquid. You've done the periodic table, right, as an extra credit. There's only there's only one metal that's a liquid at room temperature. Mercury, right. The gallium's pretty close, right? Don't say gallium though, because it turns liquid in your hand at body temperature, and that's 37 degrees. That's not room temperature. And the other one that's a liquid is non-metal, bromine. But the non-metals have a mix. Some of them are solids, some of them are gases, some of them are liquids. Actually, one of them is a liquid. So if there's a yellowish gas in there, it's probably a non-metal. So you got a metal and a non-metal. And when they react, they leave a white crystalline material. Right? So you're going to break the rule. Never taste chemicals in a laboratory. You taste it and it tastes salty. Right? So you got a metal and a non-metal combines in an ionic compound. That's why it tastes salty. Which of the following is correct? Not enough information. Well, it's maybe. 2 materials are likely to be the elements sodium and chlorine reacting to share electrons. Oh, there's the kicker. They don't share electrons. They transfer from sodium to chlorine. So that one's out. The 2 materials are likely to be sodium and chlorine, both reacting by a transfer of electrons to produce the ionic compound sodium chloride. That's probably it right there. That's the best one. D, the two materials are homogeneous compounds reacting to produce an undefinable salt. I'd go with C. Yeah, I think C is the better answer. Chlorine gas is yellowish, in case you're interested. How about this one? Fill in the table with correct information. All right. For one, let's see. One is going to be the name of NaHCO3. Right? We just named that one. I erased it, but it's sodium hydrogen carbonate, right? So that means it's either B, C, or D, sodium hydrogen carbonate. Right? We can throw A out. Sodium carbonate would be minus the hydrogen. How about 2? Magnesium, what's HCO3? Hydrogen carbonate. Right? It's a -1 charge, so we need 2 of them to balance the magnesium's +2 charge. So magnesium, hydrogen carbonate. They're using the old form, bicarbonate, HCO3. So magnesium bicarbonate, well, B, C, and D have all those, right? So now we need to go to 3, see if that'll break a tie. Sodium phosphate, right? Sodium phosphate. What's it look like? Sodium and phosphate is a polyatomic for that and that. So we need 3 of these. Na3PO4. All right. Oh, we broke our tie. Right. C is the only one that has those first 3 exactly right. And the last one, 4, magnesium phosphate. Wait a minute. There's no right answer. It says D is B. B. Wait a minute. Oh, yeah. Okay. NaPO4. Na3PO4. Okay. Yeah, I missed it. Yeah, that's right. All of those are right for B. That's it. Stop the share. And next week, we'll come back and do chapter 5, and then we'll do lab determining density. Right, so that's not a particularly involved lab. Certainly not hazardous. And we'll be determining density of different materials. We'd do it for a liquid, we'd do it for solid. We don't do gases. Not in this lab. So be sure and read through it. Make notes in it if you need to, so that you can walk in here and do it with your eyes closed. Okay. Any questions, comments that we need to deal with?
Is the chart bonus?
I'm sorry?
The chart, the 50 ways to name your compound.
Oh,
Or is
50
it
ways. 50 ways to name your compound is extra credit, and it's due on the day of the second exam. You can turn it in earlier if you want, because we've gone through how to name. There are a couple of squirrely ones in there that you might have to look up. Right, there's a peroxide in there. I think that's the only bad one. The rest of them, we've covered the rules. Did you get that one already? Oh, okay.